Linear transformations endow us with the ability to create a multitude of intricate and complex 2D and 3D games. A transformation is an operation that maps one vector space into another. For example, this transformation maps the vector space of R2 onto the vector space of R3. In order for a transformation to be considered linear, the original vector space, called the domain, must preserve the scalar multiplication and addition properties in the new vector space, the codomain. A transformation is linear whilst the following conditions are met. Properties listed on screen, like the zero vector of the domain maps onto the zero vector of the codomain, and a negative of a vector of a domain maps onto the negative of that vector in the codomain, as well as the others listed are included when a transformation is linear. Matrices are used in the contemporary game industry to allow us to compute the requisite linear transformations that allow the graphics to be displayed in a consistent format. So in a way, the matrices are a device that allow us to conduct transformations like stretching, squeezing, scaling, rotation, reflection, and orthogonal projection. The hitherto spoken of transformations help video game developers to make the games more interesting and exquisitely smooth. In a 2D platformer game like Super Mario, linear transformations are used to move the character through the world of the video game. As the player moves the character through the world, linear transformations like translation and scaling can be seen.
Matrices are used in the contemporary video game industry to allow us to compute the requisite linear transformations that allow the graphics to be displayed in a consistent format. A stretch in the xy plane is a linear transformation which enlarges all distances in a particular direction by a constant factor, but does not affect the distances in the perpendicular direction. We only consider stretches along the x and y axis. A stretch along the x-axis has the form x prime is equal to kx and y prime is equal to y for some positive constant k. Note that if k is greater than 1, then this is really a stretch. If k is less than 1, it is technically a compression, but we still call it a stretch. Also, if k is equal to 1, then the transformation is an identity, thus it has no effect. If the two stretches above are combined with the reciprocal values, then the transformation matrix represents a squeeze mapping. A square with sides parallel to the axes is transformed into a rectangle that has the same area as the square. The reciprocal stretch and compression leave the area invariant. Scaling is a transformation that either enlarges or diminishes an object based on a set scale. In Euclidean geometry, uniform scaling is a linear transformation that enlarges or shrinks objects by a scale factor that is the same in all directions. The result of uniform scaling is similar to the original. A rotation is a circular movement of an object around a point of rotation. The point of rotation for our space can be one of two possibilities, either the x-axis or the y-axis. If the axis of rotation is oriented, we can say about the clockwise or counterclockwise rotations with respect to the view from the positive semi-axis. A reflection is a mapping from the Euclidean space to itself that is in isometry with the hyperplane as a set of fixed points. Let W be a subspace of Rn and let X be a vector in Rn. The reflection of X over W is defined to be the following vector. Let W be a subspace of Rn and let X be a vector in Rn. The expression X is equal to XW plus XW perpendicular for XW in W and XW perpendicular in W perpendicular is called the orthogonal decomposition of X with respect to W. And the closest vector, XW, is the orthogonal projection of X onto W.